Hello and welcome to TidyX 49. TidyX is a screencast where we go through and explain how our code works. My name is Ellis Hughes, and you can find me on Twitter at Ellis_Hughes.
And my name's Patrick Ward. You can find me on Twitter at OSPPatrick, and you can find our screencast on Twitter at tidy_explained, or you can email us at tidy.explained@gmail.com, or you can leave comments on the YouTube channel. And we've got some great comments and feedback, so we appreciate that.
Yes, we love hearing from y'all, so thank you so much for that. And ask us questions about what we're doing here. Happy to explain what's going on here. Sometimes we just kind of glaze over some stuff that we forget to tell you while we did it. So definitely ask questions. All right, so this one, I think we've got a fun one set up here. Pat, you want to take us, tell them what we're doing this week as I cue it up?
We're going to continue on the path of sports simulations. And so we've been doing a lot of stuff with teams. We've simulated games and matchups and things like that. Today, we decided to take it to the player level, and we're going to do that with the 2019 Major League Baseball data for hitters. And so we're going to build simulations of batting average and the distribution of that batting average for each individual player, and maybe we'll continue that on next week with some other ideas as we go through. So let's go ahead and fire up some data. Yeah,
sounds good. All right, so first we load in our libraries. So we've got library tidyverse for all our data manipulation needs and plotting needs. This week, the data, rather than going to scrape it, there's actually a really handy dandy package called Lahman.
Yeah.
I actually know one of the authors that's contributed to that. So, but yeah, Lahman they take all the tables that exist in a database from
Sean Lahman is the guy that curates all the Major League Baseball data, and these folks basically do an awesome job of taking that data and turning it into our data tables.
Yep.
There's like 6 or 7 data tables within the package or something like that, maybe 5 or something like that. But pitching, fielding, I got it right here. People, batting, pitching, and fielding. And they go way back, like to 18 something or other.
So if you have a question about an R package, do question mark in the package name, it'll bring up the index page. So 1817 through 2019.
So super rich, free data out there for you to play with and work on things. So we're going to use that this week.
Yep. We're also going to load in the library GT because we're going to end up with a pretty cool GT table and Sparkline. Hopefully that doesn't give away the punchline.
And we've been on a simulation and GT kick for like the past 4 or so episodes. So,
yeah, exactly. So we're also going to set our theme for our for ggplots later on to use theme light because we just like the way that looks. And now we don't have to expressly set our themes going forward. So because the data lives inside of the R package, there's a couple ways that we can go about accessing it. The standard way, if you want this to then be available in our environment, is through data and batting, or the name of the data set you want to be using out of the package that you've loaded. So data batting makes it so that we can access that. So now we're going to assign it to df so we don't have to type batting every time because we're lazy. And so then we end up with this data frame batting, which has a player ID, the year, the stint, what the team they played on, games, at-bats, runs, hits, second base, third base hits, home runs, RBI. So super rich. There's a lot of stuff where you could probably start looking at how often does this player here hit a home run versus third base hit based on their at-bats or something like that. You could probably pull all that in and do
also
some fun.
Because it goes back so far, this is a great data set for charting trends over time, like through the dead ball era, the home run era, the juice era, like all of those things. It's really cool to see. So
gotcha.
Good one for that.
Very nice. But this week here, we are really only caring about the 2019 season. So what we're going to do is we're going to take the DF, we're going to filter to set year ID, or to keep only the cases where year ID is 2019. We're also only caring about a couple different columns in this data set. We only care about the player ID, the game, the number of games they played, the number of at-bats they had, and number of hits they ended up making. So we're going to subset to keep only those fields there just to make it simpler for cognitive load. There's also the potential that a player could have played for multiple teams, right? And so what we're going to do is we're going to group by player ID. So that way we can use a summarize, and any cases where a player may have played for 1, 2, 3 teams, who knows, we're going to go across all the statistics of games, at bats, and hits and sum them together. So that way we can get a value for the actual player themselves. And then we're going to drop our grouping so that it doesn't persist later on. And we're also going to calculate a batting average by batting average, or mutate batting average equal hits divided by at-bats. So some very quick data manipulation there, but we end up with this player DF data set here. So, there you go. We're already identifying some issues with the data that we'll touch on later on, but I guess that's a little premature there. But yeah, so we've got some fun stats here where this player here had 634 at-bats, hit 180 times, so they had a batting average of .284,
right,
which I don't know if
good
it's good or
season.
not. That's good?
That's a good season, yeah.
There you go. Good job,
Abreu. Yeah.
All right, so now we're gonna just high level look at what is the distribution of what's going on for the players. So like, what would the average be? So I could know that 284, whether that's good or bad or not. So we're gonna take player DF, we're gonna throw it into our ggplot, we're gonna set our X aesthetic to be batting average. We're gonna use a geom histogram to be able to show the actual counts, and it'll bin it by, I think it'll by default does 30 bins. So it'll slice up the range of values we have into 30 discrete bins and count up how many players were in each bin. We're gonna set the color to be pale green and the alpha to be 0.6. On top of that, we're actually going to also add a geom density. So it'll do a density, or calculate the density plot, and also add a line over our histogram. We're going to draw a geom V line where the vertical, the line is going to be, its x-intercept is at the mean of the batting average. So the mean of all players' batting average is going to be black, size 1.2, and a dashed line. So it's pretty easy to see. And then here's one thing that we haven't really talked about in the past, but geom rug. So geom rug is a really cool geom where it'll look at the values that we have there for like a histogram or density and just draw lines at the very bottom of the plot where all our values are. And so you can kind of use it to look at your histogram and density plot, but you can also look at what is the data that I have too.
Yeah,
the distribution along the x-axis.
It's like little counters along the bottom that show you basically the density of data within each of the bins, within each of the discrete bins.
Yeah, so it's kind of just another way to look at it.
Yeah.
We're going to set our labels. The x-axis will be batting average. We're not going to have a y-axis because it should be fairly straightforward what we're looking at here. The title, 2019 batting average distributions. Something. Oh. Argument 3 is empty. What did I do? Did I change something? I don't think I changed anything. So that works.
Oh, you have a comma after title in the labels. That shouldn't be there.
Derp.
There you go.
There we go. All right. So
now
we
we've got it.
All right. So here is our batting average distribution. So I can't really see much here. We've got.
Well, it looks like there is definitely a normal distribution around 2.5, and then we have a few people that have hit 100. And we have a few people
pay them all the money.
Yeah, exactly. And we have a few people that hit 0.
Don't pay them.
The thing that didn't come out here was our V line.
Interesting.
Vertical line did not show up.
Oh, because we have NAs in there.
NA.RN.
So let me tell you, the mean of an NA is NA.
Yeah, that's right. There we go.
Oh, sorry. Move forward. That's the next one.
Jumped ahead.
Ignore that. Don't look.
There we go. Okay.
There we go.
Now we see. Okay. Perfect. And we actually, so there's a ton of skew in this data. There's obviously a whole bunch of zeros that are bringing the mean down. If we use the median, it might move us closer to that 0.25. But clearly, as you would expect. There's we have a sample size problem. We have we have a large population of players that have batted a lot. We have a large population of players that have batted a little. And actually, if you run a quantile function over the number of at bats, I think you'll see like the 75th percentile is something like 266, and then it goes all the way up to, I can't remember, 600 or something like that. I mean, something, and then obviously 0 is inside. Yeah, there you go. So yeah, 0. Even the 25th percentile is 0.
So that means 25% of people have a 0 batting.
Yeah, and then 50th percentile is at 12, and then we're up to about 191, and then all the way up to the guys who just pretty much your everyday players. So one of the things that you could do is kind of get a sense for the guys that actually do play. 200 is pretty much close enough to that 75th percentile, and it's a nice round number. So I figured, let's use 200. Why not? Mm-hmm. So that was the qualifying number to look at. So everything in this next piece is the same, with the exception of filtering out only the guys that played 200 at bats.
Yeah, so this is going to make it so that you don't have those extreme cases at the end where you have 0 unless they're really bad, and somehow I've gone up to bat 200 times and have never hit a ball. I don't know how they're still there.
Now we really see, right? Now, so now you can see like the mean has moved up, whereas before the line was below 0.25. Mm-hmm. The median in that previous plot looked to be around 0.25. And now when we get to the guys that actually play, the guys that hit over 200, the mean is somewhere around probably like 0.26 or something like that. And the data is fairly normal about that. And maybe in the next video next week or maybe the week after that or something like that, we could talk about ways of addressing this with the players that have small samples. But this is just to show you that there are players that are everyday players, and they're probably everyday players for a reason. That's why the mean is just over 0.25. And the guys that aren't everyday players,
they're good hitters or something like that.
Yeah, exactly. You probably don't want that guy on the field that much or at bat that much. So, but for the purposes of our little project here, we're going to keep everybody. So we're not actually going to limit ourselves to just these guys with the 200 or more bats.
Mm-hmm. Yeah. All right, cool. So this was just like high level looking at our data, trying to understand it. So now we understand that there are players that are going to have very high or very low at bats that maybe didn't, or very high, very low at bats, but their batting average isn't very good because we just don't have a lot of data. or it's totally skewed out because we don't have a lot of data.
They batted twice and they have 2 hits.
Mm-hmm. So what we're going to do is we're going to do simulation. Like last week, we did a simulation, but we were looking at we were looking at the scoring differential.
Scoring differential, yeah.
This week, we're going to look at what is the likelihood that a player's batting average is going to be about that.
Correct. And we're going to do this, we'll do a toy simulation before we apply this to all the data. So basically, our fake player here has gone to the plate 100 times and gotten 20 hits. So he's at the 200 batting average, right? Which we calculate there, called batting average, hits divided by at bats. So we're gonna simulate this using the rbinom function. And last week we used rnorm, right, which is a normal distribution for the point margin. For rbinom, we're choosing a binomial distribution because the outcome here is a plus or a minus. It's a success or failure. You either got a hit, a 1, or you didn't. You got a 0. And so by using that rbinom function, the arguments that we pass into it are the number of times we want to run the simulation, in this case, 10,000 times, 1 with 4 zeros. The size of the sample is going to be player at bat. So basically, we're going to play 10,000 seasons for this player, with every season having 100 at bats, and the probability of this player having success, of getting a hit, in those 100 at bats in 10,000 seasons is their observed batting average. Player hits divided by player at bats. Okay, so we run that, and then we get this cool vector of 10,000 seasons, each with different. And you can see like there's a season there with 9. There's some that go up to 29 hits, 28 hits. Some that are down at 15 and 16. So you can see that given the player's probability of success, there's a range of plausible values that could have happened, right? So to get the average of the simulated individual's batting average, we just divide by the number of observations in each season. And so we take the mean of the seasons divided by the mean of the simulations divided by the at-bats. And we get 0.2, which is 200, which is the batting average that we observe for this player. And the reason why we have this cool distribution is to then be able to calculate our quantiles. So how much certainty can we have in this player who is a 200 hitter? And with only 100 at-bats, obviously, there's a broad range of probable values. And as this player bats more, then that'll obviously become tighter and tighter. So we're essentially just creating a simulation of random draws of successes and failures based on what we've observed this person to do and the number of times that they've been observed to do it. And like I said, maybe next week we'll handle some of the guys that have low samples in a different way. But right now, we're just going to run this over the entire population. So we're going to go 10,000 times and get our 90% confidence intervals. So we're going to take our data set, our player DF. This is everybody, whether you batted 0 or 1 or 681 times. We're going to filter out all the at-bats or 0, because if you didn't at-bat at all, you had no chance to have success or failure, so we have no idea what you are. We're going to run this using the rowwise function, which behaves like a fancy way of saying group by, which is basically saying group by each row. We're going to apply this to each row as it goes through the data set. And what we're going to apply is what takes place in this mutate. So we're going to create simulations, and this is the exact same rbinom that we did above. We're just wrapping it in this list. And the idea here is that we want to store all of the 10,000 seasons for that individual and just nest it in a list at each row for each player that we run this on. We calculate the average of their simulation the same way we did above, and we calculate the confidence intervals the same way we did above. This time, though, we just split out each column low and then high so that it's nice and clean looking. And then we ungroup so that that doesn't affect anything going forward. The grouping of row-wise doesn't affect anything going forward. Okay.
There we go. So now we've simulated 1,000 seasons for
every 2019 player.
Every
had
19,
at least one at bat.
983 players.
And that was super fast.
Yeah, that went pretty quickly. Thankfully, R has a lot of really cool under the hood fast stuff going on for their base R functions.
Yeah, and so you can see the listed simulation data.
So this is the 10,000 seasons simulated.
Correct. And so if you wanted to take one player, you could unnest that and look at that player. We actually, you want to go ahead and do it? Yeah.
Let's do it for the first player.
There you go. Yeah, there you go.
So they hit from anywhere from 192 to 06.
So what could we do with this list of simulations for each player, Ellis?
Well, we could make a table to try to visualize this, and because tables are a data-viz tool, and try to understand, like, maybe there's a player you're particularly interested in, you want to look at, how does he compare against a couple other players in it, or just, take a random draw of, like, what does it look like? I don't know. Yeah. Who knows? And this is just kind of a fun way to look at your data. And so what we're going to do is we're going to take this simulated data set, and we're going to sample n. So sample n is a function that comes out of dplyr, where where we're going to say this is the number of samples that we want to keep out of it. And keep in mind, this also needs to be, this is done group-wise too. So if you've grouped your data frame, it'll subset n by each group. So that's kind of a cool trick. If you know that you want to be pulling out 10 records for each group, you don't have to try to make sure to stratify it. You can do it using this. So sample n, so we want to keep 10 rows. We're going to replace equals false because we don't want to draw the same player twice accidentally. And we're actually, we're using this weighting here. So weighting when you're sampling is saying what is the probability of pulling that player. And so if you don't have a weighting value in there, that means every player has an equal opportunity to be drawn. But we wanted to make sure that we could see a wide variety of players shown up, but giving preference to players that had a high at-bat per game. So they could have played in 5 games, but if in those games, they batted
4 times each.
20.
Their ratio is 20 at bats per game.
And so that's good, and so they'll be more likely drawn. So that's just that's for us for a visualization, and maybe if something you're doing some simulations going forward, so you can do that. Next, we're gonna once again use rowwise, but this is so that we can do some fun stuff here. So we're gonna rowwise, so basically group by each row, and we're gonna create a vector of confidence interval, or create the confidence intervals low and high, because typically you don't. At least I've found when you're showing your confidence intervals in a table, you don't leave them as two separate columns. You kind of just place them together. It's like, here's the low and high confidence intervals, FYI. So we're going to do paste, square brace, round the low confidence interval to 3 decimals, round the high confidence interval to 3 decimals, square brace. So people understand this is confidence intervals. These are not the actual values. But then we're actually going to add a spark chart. So we did spark charts a while ago.
Within the first 10 episodes.
Yeah, so we did spark charts with that. And so we thought it might be interesting we still have those simulations. We have that data there. Let's have a spark chart to show, to be able to visually compare across the different players what that looks like. And so we're going to do simulate. We're going to spark chart, and then we're going to throw in our simulations. We're going to use the type box. So that's then going to create essentially a box plot of our simulations. And we're going to store that in the Spark Sim field. We're going to ungroup it again, because once again, we don't really want it to be grouped going forward. We're then going to add a left join here to add in the actual names of the players, because if you remember, we had player ID, and that was it looked like their last name and then some
last name, first 2 initials,
and then some identifier. Yeah, so that way if there's a duplicate, that they're able to distinguish that. But Lahman has a people data set there that has the players' names as well as the player ID and a bunch of other information around the player too. So this time, rather than using data to access the data table, we're going to use Lahman : people. This means, so this is telling R to go into the namespace of Lahman and pull out the people data set. We're then going to throw it into a mutate to paste together the first and last names, and we're only going to select player ID and this new name field that we've created, and left join. So this is going to take this Lahman people special data frame that we've made and paste it on to the end of the data set that we're currently working with, and only keep the matches. Only keep the matches without removing any of the left data frame, if that makes sense. Joins are a strange thing sometimes. And then we're going to select to remove low CI, high CI, player ID, and simulations, because we no longer want those in our data set for creating our table. So, Patrick, you want to take us through the actual GT?
Okay, yeah. So we did GT tables, I think, 2 times ago, or maybe last week. I think we've done them the past 4 weeks. So really cool way to make a table. We start by just calling the GT function, which is the basic function of GT that's going to get you off the ground and put a table on the canvas. And we're going to set the row name column to the name of the person. So rather than having name be an explicit column in the data set, it's just going to throw that over to where the row names would be, and that's going to be the names of the people. The next one, a tab header, is how we put a header on this thing. So we're going to title it MLB player averages, and we're using a little bit of Markdown there with the stars. The double stars around MLB is going to give us a bold. And the subtitle, 2019, a single star, gives us an italics. So MLB will be bold, 2019 will be italics, and player batting average will be normal as you see it on the page. Then we're going to take care of the column labels. So we want to have explicit labels because the underscores look kind of silly, and we want this to look clean. So batting average, we're actually going to call it batting average with a break. So it's going to be batting on one row and then average on the next row, basically like a double row title there. We're using the HTML wrapper here. You could also use the MD wrapper here in calls label and make that bold if you wanted, or italics. do whatever you want, really. But we use the HTML wrapper in this example. The sim average, we're going to call it simulated batting average with a break between simulated and batting average. The confidence interval, that column that we created that has the confidence intervals within brackets or square brackets, we called it 90% confidence intervals.
Just updated to 95. Realized it was actually 95% confidence interval.
Was it? I thought we did 0.995 to 90%, right? There's 10%, 5% on each end. So if it was 95, it'd be 0.975 and 0.025, right?
Sure.
Yeah. 90%.
I'll go with you.
And then Spark Sim. So this is our simulated data. We're going to call it simulated break BA box plot for batting average box plot. The format numbers function is a handy dandy way of just telling it that, hey, batting average and sim average, round it to 3 decimal places, please. And then the data color, we are going to put in a sort of Excel conditional formatting type of looking thing here. The variables that we're going to do it on are the simulated averages. The colors we're going to borrow from the scales package, this call numeric function. And the palette is red, white, and blue. So red at the low end, white in the middle, and blue at the high end. And then the domain null, I can't remember why we
still couldn't figure that one out.
It's always there. Yeah, it always has to be there, and I can't figure it out.
Yeah.
And then format Markdown columns. It's going to be vars Spark Sim. So this is, you have to do this in order to basically set up the Sparklines that you're going to set up.
It then wraps it basically in HTML, so it understands that this is HTML and JavaScript that we're passing to it.
Correct.
So
and now,
all right.
go
so
ahead
now we've created our GT table, but Sparklines is HTML. It will not render by default just printing out this table. So we have to add a couple of dependencies and tell it how to behave. So we're going to use GT and basically convert our GT table into an HTML table for us. So we're going to do that. Then we're going to add a dependency using HTML tools. So HTML tools attach dependencies. We have the HTML of our GT table. Then we're going to do HTML widgets, get dependency Sparkline. So this will get the dependencies for Sparkline and add it into player AB GT HTML. Sorry, this is a little this is getting into HTML widgets and some weird stuff. It's pretty fun if you play around with it a lot, but it's also just a lot of hassle. To be able to then go print GT player at bat GT HTML, browse interactive. So this means that it'll show up as an HTML and we can interact with it. Print and
zoom in. Sweet.
And here we go.
So now,
So we've got a random smattering of some players here, anywhere from 230 to 447 at bats, 611 from Kevin Pillar, down to 9.
9 with 0 hits.
With 0 hits here, so we don't have a lot of confidence in this person right now.
And then we have a cool simulated box plots.
Yep, we have our Sparklines here on the right here, so you can kind of visualize and go, ooh, wow, he's way down here. And you can kind of see, we can rerun this again in a sec, because you can see basically how big these boxes are to show how confident. It's like another pseudo look at how confident we are in the players in their in their ranges here. So there's that. So it's just, it's a good way. Games at bats, batting average, simulated batting average here. You can see that they're new lines there. The confidence intervals. So, just a fun way to look at this data. I mean, and, the higher at bats they've had, the closer the simulated batting average and the actual batting average are. As you can see here, 56 games. It's slightly different here, so that's kind of and
so every time we run this, because we have it as a random, every time we run ours, you'll get a new subset of the population.
Yep. So now you can look at this. So then you can also see how the let's zoom out. No? Is it going to let me zoom out? No. But here you can see that this is a wider range. So this Drew Butera Could be anywhere from 70 to 256.
Yeah.
Who knows?
Yeah.
And so they're all, that's the batting average. So all over the place. But anyway, yeah, it's a fun way to look at your data. Add Sparklines into your GT table and doing some fun stuff with that.
Yeah. Pretty cool.
Yeah. And I think with that is all the content we have for this week. So thank you all so much for joining us and learning a little bit more about simulations and moving down from the team level down to the player level, and as we continue to explore all this data.
Yeah.
But yeah, so thank you for joining us. My name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward, and you can find me on Twitter at OSPPatrick. And the screencast is on Twitter at tidy_explained, or our inbox is at tidy.explained@gmail.com, or you can always comment on the YouTube screencast itself, and we'll get back to you.
Thank you so much, and keep on exploring your world.